Pluto, once hailed as the ninth planet in our solar system, has a history full of intrigue and change. It is located in the distant Kuiper Belt, a vast region of hundreds of thousands of small icy planets and asteroids. For 76 years, Pluto held its place among the great planets, attracting the fascination and admiration of astronomers and the public. Named after the Roman god of the underworld, Pluto's journey from planet to dwarf planet has been one of scientific discovery, debate, and changing perspectives. The history of Pluto began at the beginning of the 20th century, when astronomers were looking for a planet beyond Neptune that could explain disturbances in the orbit of Uranus. This hypothetical planet, called Planet X, ultimately led to the discovery of Pluto. On February 18, 1930, Clyde Tombaugh, a young amateur astronomer working at the Lowell Observatory in Flagstaff, Arizona, photographed a distant object that matched the predictions of Planet X. Tombaugh's discovery was soon confirmed, and the new celestial body was called Pluto, proposed by an 11-year-old girl, Venetia Burney, from Oxford, England. The discovery of Pluto was celebrated worldwide and quickly became a beloved member of the planetary family. But its small size and unusual orbit, highly elliptical and tilted relative to the plane of the solar system, made it an oddity among the planets. Despite these features, Pluto remained the ninth planet for several decades. The reclassification of Pluto was triggered by the discovery of other trans-Neptunian objects, TNO, in the Kuiper Belt. In 1992, astronomers David Jewitt and Jane Liu discovered the first of these objects, 1992 QB1. This discovery marked the beginning of a new era in the study of the outer solar system and led to the detection of many other TNOs. Among those discoveries was the dwarf planet Eris, discovered in 2005 by a team led by Mike Brown. Eris, originally named after Xena's TV character Xena, warrior princess, was found to be larger than Pluto, reigniting the debate over the shape of the planet. In 2006, the International Astronomical Union, IAU, held a conference in Prague to address this issue. After extensive discussion and debate, the IAU introduced a new definition of a planet. According to this definition, a planet must orbit the Sun, be massive enough to assume a nearly round shape, and clear its orbit of debris. Pluto met the first two criteria, but failed the third because it orbits other Kuiper Belt objects. As a result, Pluto was reclassified as a dwarf planet, sparking public outrage and scientific debate. Despite the reclassification, Pluto continues to be a subject of great interest and research. One of the most important milestones in Pluto exploration was the New Horizons mission launched by NASA in 2006. New Horizons was the first spacecraft to visit Pluto, and its journey lasted almost a decade. On July 14, 2015, New Horizons made its closest approach to Pluto, providing humanity with the first detailed images and information about this distant world. The data returned by New Horizons changed our understanding of Pluto. The spacecraft revealed a world with a diverse and active surface, with nitrogenous rocks, pieces of methane ice, vast plains, and towering mountains. One of the most striking features was a heart-shaped region known as the Tombaugh region, named after the discoverer of Pluto. That area is home to Sputnik Planum, a vast plain of nitrogen ice that appears to be geologically active, with surface changes caused by glaciers and convection cells. New Horizons also provided evidence for the existence of a subsurface ocean beneath Pluto's icy crust. The discovery of a chaotic landscape that seems to be the result of asteroid collisions suggests that the interior of Pluto may contain liquid water. This discovery has significant implications for the possible habitability of icy worlds in the outer solar system. The atmosphere of Pluto, which consists mainly of nitrogen, methane, and carbon monoxide, was another area of focus for New Horizons. The spacecraft monitored seasonal changes in the atmosphere as Pluto orbited the Sun. When Pluto is closer to the Sun, its surface ice sublimates and changes from a solid state directly to a gas, creating a temporary atmosphere. As Pluto moves further from the Sun, the atmosphere freezes and falls back to the surface. These observations provide valuable information about the behavior of the atmosphere in extremely cold environments. The mission also explored Pluto's moons, revealing surprising details about these tiny worlds. Charon, Pluto's largest moon, showed a rugged landscape with deep cracks, high cliffs, and a dark reddish-brown region at the North Pole. The smaller moons, Nix, Hydra, Kerberos, and Styx all had unique characteristics and orbits that added to the complexity of the Pluto system. The New Horizons discoveries have changed our understanding of Pluto and its place in the solar system. The mission revealed that Pluto is a dynamic world with active geology, a diverse surface, and a complex atmosphere. These observations challenge the traditional view of Pluto as a cold dead rock and suggest that even distant dwarf planets can be active and interesting. In the years since the New Horizons flight, scientists have continued to analyze the data returned by the spacecraft. This ongoing research has led to new questions about Pluto's geology, atmosphere, and potential to support life. One of the main areas of interest is the possibility of an underground ocean. Evidence of liquid water beneath Pluto's icy crust has significant implications for our understanding of the potential for life in the outer solar system. Similar subsurface oceans have been proposed for other icy bodies, such as Jupiter's moon Europa and Saturn's moon Enceladus, where liquid water is thought to exist beneath thick ice crusts. Pluto's atmosphere is also still being intensively studied. The seasonal changes observed by New Horizons offer a unique opportunity to understand how the atmosphere behaves in extreme environments. As Pluto moves around the Sun in its 248-year orbit, its atmosphere undergoes significant changes, moving between a thin gaseous state and a frozen solid state. These findings will help scientists develop models of atmospheric processes in other icy bodies and contribute to our broader understanding of planetary atmospheres. Another area of interest is the geological activity of the surface of Pluto. The discovery of nitrogen glaciers, icebergs, and vast plains suggests that Pluto is much more geologically active than previously thought. Cryovolcanoes, volcanoes that erupt from icy materials rather than molten rock, suggest that internal heat sources drive geological processes on Pluto. These findings prompted scientists to rethink the thermal evolution of icy bodies and the possibility of similar processes on other distant worlds. The study of Pluto's moons has also yielded fascinating insights. The rugged terrain and signs of past geological activity represent Charon's stark contrast to Pluto. The dark reddish-brown region of Charon's North Pole, known as the Mordora Macula, is thought to consist of tholins, complex organic molecules formed when sunlight interacts with methane and other simple carbon compounds. The presence of tholins on Charon and other solar system stars raises questions about the presence of organic chemistry in the outer solar system and its possible role in the origin of life. Pluto's smaller moons, Nix, Hydra, Kerberos, and Styx, also provide valuable information about the formation and evolution of the Pluto system. These craters have irregular shapes and chaotic trajectories, suggesting that they may have been captured or formed by impact debris. Studying these moons helps scientists understand the processes that form lunar systems and the dynamics of small bodies in the outer solar system. Looking to the future, scientists want to build on the discoveries of New Horizons. Possible follow-up missions to Pluto could provide more detailed observations of its surface, atmosphere, and moons.
Such missions may include orbiters, landers, or even mock return missions that provide opportunities to study Pluto and its surroundings in more detail. Advances in technology and spacecraft design will play an important role in enabling these future studies. Apart from Pluto, the Kuiper Belt remains a rich research area. The region is home to a huge number of ice bodies, many of which are still unknown. Future missions to the Kuiper Belt could help scientists better understand the formation and evolution of the outer solar system. By studying these distant objects, scientists can gain insight into the processes that formed the early solar system and the distribution of materials in the protoplanetary disk. The study of Pluto and the Kuiper Belt also has implications for the understanding of extraplanetary systems. Many of the processes observed in the outer solar system, such as the formation of ice bodies and the presence of underground oceans, are likely to occur in other star systems as well. By studying Pluto and its neighbors, scientists can develop models that inform the search for exoplanets and the possibility of life outside our solar system. The debate over Pluto's classification as a planet is still unfolding. Some scientists argue that the current definition of a planet is too restrictive and does not accurately reflect the diversity of objects in our solar system. They suggest that a more comprehensive definition, based on intrinsic properties rather than orbital dynamics, better accounts for planetary complexity. This ongoing debate highlights the dynamic nature of scientific classification and the importance of constantly reassessing our understanding of the cosmos. In conclusion, Pluto's journey from planet to dwarf planet and beyond is a testament to the evolutionary nature of scientific discovery. From Clyde Tombaugh's discovery in 1930 to amazing observations by the New Horizons mission, Pluto has fascinated scientists and the public.